Okay, so these are the 6.2 notes, and we're going to be looking at transforming and combining random variables. All right, so first thing we want to look at is multiplying by the mean and standard deviation of a random variable by a constant. Now, I'm not going to be going into a ton of detail in these notes. The book does a really good job explaining why all of this works, so I'm not going to be giving you proofs. I'm not going to be going through and kind of giving you an example the way the book does. The book does a really good job of breaking down why these rules apply. They give some really good examples, and they explain the entire shapes of histograms and how those are distributed, so that way we can have these rules. And again, these rules are basically the exact same rules we looked at in chapter 2 when we started looking at z-scores, calculating z-scores, looking at normal distribution, so on and so forth. So these are basically, again, like kind of in the spirit of 6.1, it's kind of the idea of we're taking chapter 2 rules and we're applying them to probability now. So when we divide a random variable by a positive number, we multiply and or divide the measures of center and location, so the mean, medians, quartiles, percentiles, any specific number that you have, any like hard number that comes from the data itself, you multiply by that number. You also multiply that same number by any measures of spread. So your interquartile range, the range itself, the standard deviation, they all get multiplied as well. And those are the exact same rules from chapter 2. Now we're just doing it with now we're just doing it with rules from probability. And this does not change the shape of the distribution. Remember, no transformation we do changes the shape of the distribution. The distribution shape is always the same. We're just shifting it one direction or the other, or making it wider or more narrow. So if you multiply or divide, you're kind of changing the shape of the distribution in the sense that like you're making it a wider or narrower fit. However, it's still going to have the exact same shape. It's just going to be wide or narrow. All right, then if you add or subtract a constant to the mean and standard deviation, the exact same rules again as chapter 2, so it adds to specific values. So any measures of center, so your mean, the Q1 value, the Q3 value, your max, your min, you add that number to all of them, you add it to your median. It doesn't change the shape of the spread, it doesn't change your values of spread. If all you're doing is adding numbers, all your numbers are getting shifted the exact same amount up. The width of your distribution stays the exact same. So because of that, your measures of spread don't change at all. So your IQR is still going to be the same distance. Your range is still going to be the same distance. Your standard deviation is still going to be the same distance. So if you're adding, it only changes the mean, not the standard deviation. All right, so we're already into a check for understanding. Again, the book breaks this down really well, so I'm not going into a ton of detail in these notes. I'm kind of just filling in some gaps and giving some extra examples. All right, so you should recall this from 6.1 notes. We're looking at this auto dealership. They keep track of sales made during each hour of the day. Let X be the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of X is as follows. So it has a mean of 1.1 and a standard deviation of 0.943. So let's suppose the dealership's manager receives a $500 bonus from the company for each car sold. Let Y equal the bonus received from car sales during the first hour on a randomly selected Friday. Find the mean and standard deviation of Y. So here all we have to do for number 1 to find the mean of Y, which is denoted by U of Y, we're going to do 500 times 1.1, and I know I should be able to do this in my head as a math teacher. This is going to end up being 550. I'm going to double check it on my calculator because I'm paranoid like that. And yeah, it's 550. So our mean is $550. This manager can expect to make $550 on an average Friday. So that's what they make. The standard deviation, that's going to end up also being that 500 times that 0.943. And this is going to end up being 400 $71.5. So the typical amount of money he'll make in that time typically varies by $471.5, which these kind of make sense. If he's selling a car, he's making $500. If he's not selling a car, he's making pretty close to $0. Again, this is not perfect because we're talking about averages, and obviously averages don't apply here, but this is kind of everything that varies out for him. All right, so to encourage customers to buy cars on Friday mornings, the manager spends $75 to provide coffee and donuts. The manager's net profit on randomly selected Friday is the bonus earned minus the 75. So find the mean and standard deviation. So in this case, we're now denoting this by T. So the mean of T is equal to 550 minus 75. So the mean of T is now equal to $475. That's going to be the average amount of money he makes because he is apparently buying some of the best donuts on the planet, along with some really, really fine coffee to try to encourage sales. The standard deviation of T, though, let me write this in a better color. So the standard deviation of T is going to be the exact same thing as the standard deviation we found up here. When we're subtracting that money, it makes no change to it. So this is going to vary by $471.5. So subtracting money from this does not shift that standard deviation. It's still going to vary by the exact same amount of money because all we've done is shift everything down by $75. The variance between how much it changes, the typical distance from that mean, is still going to be that $471.5. All right, so the book has a pretty good idea of this. Now they're just saying, like, we can think about this as a linear transformation. We can turn this into y is equal to a times bx. B represents a number that you're multiplying by. X represents your variable. A represents a y-intercept, or in our case, either something that you're adding or something that you're subtracting from that multiplier times that value. And you can even think if all we're doing is adding, that multiplier is just 1. So if all you're doing is adding a number, that b value is 1. If all you're doing is multiplying, then that a value is 0. So it works out either way. Now, if you want to figure out what your mean is, it's just a plus b times the mean. And if you want to figure out what your standard deviation is, you just do your absolute value times the absolute value of b times the standard deviation of x. And we have to do the absolute value because b can be a negative number. We might be multiplying it by a negative, in which case we don't report standard deviations as negative. So we're going to do the absolute value of b in those cases. This is kind of straightforward. And just taking what we already have done in the previous 3 slides and putting it all together is kind of one slide. All right, independent random variables. So if knowing whether any event involving x alone has occurred tells us nothing about the occurrence of any event involving y and vice versa, then x and y are independent random variables. So the book kind of talks about how we would have to go through and figure out and make our determination of what is an independent random variable. So for example, I've got fast food chains in 2 different regions. So let's say fast food sales of, like, we're talking about McDonald's. Let's say the McDonald's on Douglas Avenue is going to be independent of the sales of a McDonald's in Phoenix, Arizona. They're not going to have any impact on each other. Let's consider like everything's happening normally. We're not considering like we find out that McDonald's has an E. coli outbreak. Like, yes, there are cases where it's not independent when there's like some national shifts happening or there's national news surrounding McDonald's. But on your average, like, stereotypical day, there's nothing about the McDonald's in Racine that really has any influence over the McDonald's in Phoenix. I wouldn't do the McDonald's on Douglas compared to, the McDonald's on Highway 20. Because those might not be independent. We're talking about people might drive from Mount Pleasant to Caledonia. I guess that's in Racine. But people might be driving on both Highway 20 and on Douglas Avenue, so they might be stopping at either one of those McDonald's. There might be some factors of how close somebody is, etc., that changes who goes to what McDonald's. So in that case, me personally, I'm not going to say they're independent. Now, somebody might argue that they are, and there might be better statisticians that make that argument. But what we could probably say definitively is that there is nothing going on in Phoenix, Arizona that would influence sales of a McDonald's on Douglas Avenue in Racine. Any like gambling thing, again, not poker, but when we're talking about roulette, craps, coin flips, dice rolls, spinners, those are all independent. Just because something happened on one does not affect the outcome of the next. The outcome of the next, every single time, it changes. They're always independent. They're always changing. So all of these are independent random variables. Some examples of things that aren't independent are like your GPA and ACT score. They're usually correlated. So usually people who have a high GPA tend to have a high ACT score. People with a lower GPA tend to have lower ACT scores. Height and weight of a population, those are somewhat correlated. So again, like, I'm never going to be under 100 pounds. Like, there's just a certain level of weight that my 6'6" frame has to have on it, just via like organs and bones. So it's dependent on each other. Just like for a person that's under 5 foot, the chances of them breaking 180, 190 pounds is going to be pretty low. It's going to take it takes a lot for those weights to kind of vary a lot from heights. Now, there's going to be some variance between heights. I've met people who are my height that are 160 pounds. I've met people that are my height that are 400 pounds. Yeah, there's a lot of variance within that height, but still, I would say that your average person at 6'6" is going to weigh more than your average person at 5'1". So height and weight aren't going to be independent variables. So we can add independent variables. The book does a good job of describing those brother and sister and their car adventure business that they both own, like weird franchises of. It's a weird example, but I think it does a good job of explaining it all. If you have two random variables, you can add the means of those two random variables. So the mean of two random variables, if we're combining them, okay, it's the exact same as we just take the mean of one and we add it to the mean of the other. It gets a little bit different when we start talking about standard deviation, because we can't just add those standard deviations together. It doesn't work that way. But what we can do is we can add the variances together. And what we have to remember is the variance is the standard deviation squared. So you might be asking, Mr. Yehlen, they're giving us the standard deviation in a lot of these problems. How do we find the variance? You take that standard deviation, you square it, you add it to the other standard deviation squared, and then you take the square root of that. So if you want to figure out, so I like to kind of like move this to the next step, which would be the standard deviation of t is going to be equal to the square root of the standard deviation of x squared plus the standard deviation of y squared. So this is the formula. This is the formula for variance. And then to figure out the standard deviation, you take the square root of your variance. So we can add our variances together. We can't add our standard deviations together. So let's go ahead. Let's go back to this auto dealer. So now we're also adding in y as number of cars leased. So now we have number of cars sold and we have number of cars leased. And these are still based on Friday. Based on previous record, the probability distributions of X and Y are as follows. So we've got that mean of 1.1 and that standard deviation of 0.943. And we have that mean of 0.7 and that standard deviation of 0.64. So I want to find and interpret the mean of t, given that t is X plus Y. So this is really easy. The mean here of t is that mean of X plus that mean of y, so this is equal to 1.8. So on an average Friday, combined, this dealership is selling and leasing 1.8 cars on a Friday morning. On average, this is a typical Friday for them. I want to figure out what the standard deviation of t is. All right, this is going to be a little bit more complicated. So what I have to do here is the standard deviation of t is going to be equal to the square root of 0.943 squared plus 0.64 squared. So I'll go ahead, I'll pull out my handy dandy calculator here. So I've got 0.889 plus 0.4096. I still want the square root of this, so I've got the square root. So I'm looking for the square root of 1.2986. And so my standard deviation of t here is 1.14 cars. So in any given Friday morning, you have a mean of 1.8 cars that are sold or leased, and then the typical difference from the mean is around 1.14 cars sold or leased. Last thing here is trying to figure out the dealership's manager receives a $500 bonus for each car sold and a $300 bonus for each car leased. Find the mean and standard deviation of the manager's total bonus. So the mean here, to figure out the mean, I'm going to call that B for bonus. This is going to be equal to 500 times 1.1 for the cars sold plus 300 times 0.7 for the cars leased. So we've got that $550 already for the cars sold. And then we have $210 for the cars leased. So $760 is the mean amount of money the manager is making on any given Friday morning. So on any given Friday morning, the typical amount of money the manager can expect to make on average throughout the year, he's making about $760 in revenue. This is not including that $75 he's spending on the coffee and donuts. Standard deviation of B is a little bit weirder because first we have to figure out what the standard deviation of the cost is. So now I've got to do, this is the square root of 500 times 0.946 squared plus 300 times 0.7, and that's not 0.7, that's 0.64. So we have to multiply those original standard deviations by the numbers that their multipliers are, and then we have to square them. So it's an extra step, and we have to make sure that we're keeping these separate. I cannot just multiply those numbers out, so we'll go ahead. 500 times 0.946 is 473. 300 times 0.64 is 192. Add these two numbers together. And then we'll take the square root of that number. And we will find that the standard deviation of his profit, so we'll call that bonus, is $510.5. So he's making on average on Friday about $760 on an average Friday, and that amount of money typically varies by about $510.50 on any given Friday. So that's kind of how it shakes out for this manager in terms of him making and or losing money. All right, now rules for the difference between the two random variables. I don't think it should come as a shock that if we can add the means to figure out how much money, or if we can add the means to figure out what is the means of two things combined to figure out the difference, we can subtract the means. So the mean difference is equal to the mean of one minus the mean of the other, whichever one we're looking at. Now, the book does a really good job of explaining this, but when we look at the variance ends up being the exact same thing as the variance of things combined. That's because the ranges of the difference and the ranges of the combinations end up being the exact same value. So whatever the range is for the combined is the exact same as the range for the difference. And since those ranges are the exact same numbers, you end up with the exact same variance and the exact same standard deviation. So the variance formula and the standard deviation formula don't change for combining two random variables versus the difference between two random variables. So we got to check for understanding to look at it. Again, exact same thing, cars leased, cars sold. We know our means, we know our standard deviations. It wants us to define x and y of the difference is x minus y, so find the mean difference. Our mean difference here is 1.1 because that's the mean of x, minus 0.7 because that's the mean of y, so this is 0.4. What is this interpreted? This means that on Friday, on average, we sell 0.4 more cars than we lease. So let's say that we're talking about 10 weeks here. That means on average over those 10 weeks, we've sold 4 more cars than we've leased on Fridays. We sell 0.4 more cars on Friday on average, more than we lease typically. All right, compute the standard deviation of D here. That standard deviation of D is going to be the exact same thing as this standard deviation of T up here, which we found. The standard deviation in the variance is no different than the standard deviation and variance is no different in combining than it is in the difference. So we've got the exact same standard deviation up here. I don't need to do any work. I know it says to do the work, but I'm not going to. I'm not going to waste my time with that. So it's 1.14 cars. This is the typical amount that it varies. So we've got a difference of 0.4 cars, but that difference varies by 1.14 cars every Friday. All right. Again, this dealership manager with his bonus, $500 bonus for each car sold and $300 bonus for each car leased. Find the mean and standard deviation of the difference. So right away, I'm just going to go ahead, the standard deviation here. So we'll call this again the standard deviation, the bonus. It is unchanged because the variance rules are the exact same variance rules because that range is the same. We would do all that same multiplication. So I can say that the standard deviation of the bonus is going to be $510 for this difference. For the mean difference, what I would do here is I would say 500 times 1.1 minus 300 times 0.7. So I've got 550 minus 210. So this is $340. So the mean difference is $340. The manager is typically making $340 more off selling cars than he is off leasing cars. On an average Friday, that's how much he should expect to make more from selling those cars. But that does vary by $510.50. That's the typical distance from the mean. All right, last thing, normal distributions. If two random independent variables are normally distributed, we can apply all the same transformations and the resulting distribution will also be normal. This only works if they're both normal. If you're looking at two things, one is normal and the other is not, that distribution is not going to be normal. But adding two normal distributions together keeps that new result as normal. So then when you're going through, you can use the means and the standard deviations for z-scores, and then you can calculate probabilities. Figuring out what those means and standard deviations are the exact same rules that we just applied here. Any transformation that you apply to it, when you add them to figure out your mean, you'll add your two means. To figure out your standard deviation, you'll calculate your variance. You'll combine your two variances, and then you'll take the square root of that to get your standard deviation. All right, you guys have a homework assignment. Reach out if you have any questions or concerns, and have a great night.